In this video, you will use the Metaneuron Simulations program to run virtual action potentials under different conditions. First, download Metaneuron at www.metaneuron.com. You may pause this video as necessary. In this video, I will walk you through the process of simulating the following experiments: generating a resting membrane potential, producing an action potential, analyzing the effects of temperature on action potential, determining the minimum stimuli amplitude for an action potential, and lastly, studying refractory periods. We will start by simulating the membrane resting potential. Activate the Metaneuron window and press F1 on the keyboard to start Lesson 1. Enter the sodium and potassium ion concentration values. Next, enter the sodium and potassium ion conductance values. For your convenience, the values required for this step have been provided below. From here, this is what you should be seeing on your Metaneuron Simulations program. In the top control panel, in the purple box is where you should be entering the values previously mentioned. In the bottom is the simulation output. Let's review it briefly. The yellow trace is the membrane potential. The green trace represents the sodium potential in millivolts. And the cyan trace represents the potassium potential in millivolts. From this simulation, what do you think is the final cell resting membrane potential in millivolts? Next, we will simulate the membrane potential of a cell during an action potential. Activate the Metaneuron window and press F4 on the keyboard to start Lesson 4. You may use the default values in Metaneuron for now. Once the simulation is complete, analyze the graph below the control panel and familiarize yourself with the graph. When you are ready, select Show Ion Conductances under the Conductances and Currents section. Analyze the ionic conductances on the graph of sodium and potassium ions. Next, select Show Ionic Currents under Conductances and Currents. Analyze the ionic currents on the graph of sodium and potassium ions. This is what you should be seeing on your screen. Take a moment to answer the following questions. When conductance is shown on the graph, why are both ionic traces positive? When ionic currents are shown, as seen in this screenshot here, why is the potassium ionic current trace positive, while the sodium ionic current trace is negative? Lastly, what do you think is the cause of the upwards inflection in the sodium current, which is highlighted in the purple circle? In this exercise, you will analyze the effects of temperature on an action potential. First, activate the metaneuron window and press F4 on the keyboard to start Lesson 4. Press Ctrl L to reset the lesson back to default values. Select the Range checkbox under Temperature. Enter a starting value of 5, an end value of 25, and increments of 1. Press 3D Graph to generate a 3D model for easy viewing. Here is the control panel. As per the previously mentioned steps, you want to check the checkbox in the temperature section, which is in the upper right and in the purple circle. Next, you want to input the range values, which is in the purple box on the lower left, with a starting value of 5, end value of 25, and increments of 1. Lastly, you want to press 3D Graph to generate a 3D plot. Review the data generated in your 3D plot. According to the simulation, what is the maximum temperature in Celsius required to generate an action potential under the default settings? What trends in the action potential do you notice as the temperature begins to decrease? We will now utilize metaneuron to determine the minimum stimuli required to elicit an action potential. First, activate the metaneuron window and press F4 on the keyboard to start Lesson 4. To return to the default values, press Ctrl L. Inside the Stimulus 1 panel, test different ranges of amplitudes to determine the minimum stimulus for an action potential. Hint: use the range function by selecting the checkbox to the right of the amplitude field. Once your simulation is complete, please answer the following question. What is the minimum amplitude required to elicit an action potential, according to the simulation? We will now utilize metaneuron to determine the refractory period required to elicit a second action potential. Press Ctrl L to reset Lesson 4 back to default values. Increase the sweep duration to 15 milliseconds, which will extend the time scale of the simulation. Select the On checkbox under Simulation 2 to add a second stimulation. Under Stimulus 2, set the delay time to 10 milliseconds and press Enter. Confirm on the screen that there is a second action potential. Begin varying the delay time to determine the refractory period. Hint: you may use the range function. Once your simulation is complete, please answer the following questions. What is the refractory period in milliseconds? Is this a relative or absolute refractory period?